Hi. That was the circuit that we examined before, and we said this circuit unstable. Since it is unstable, the homogeneous solutions becomes infinitive in a short time, so we cannot observe the particular solution. Now I am going to change now. I'm going to make this circuit stable by changing this coefficient value here. Let me make it in red. So that coefficient is 1/10. If I replace this coefficient, that means changing the element parameter. If I make it 1/40 instead of 1/10, that's going to become stable. So in here, unstable. In here, stable. So we are saying now, we are not going to take this one, we are going to take this one. Okay, color make it. Okay, so just remind you, that was VC, that is capacitor voltage, isn't it? So that is capacitor voltage as well. So this dependent current source depends on this capacitor voltage. So that VC is also that VC. So if you remember, we have chosen this capacitor current reference downwards in order to make it proper for the passing sign convention, isn't it? It's going to be mutually acceptable. So that is the node that we are dealing with, and the current of this inductor, I'm going to choose the current reference upwards. The reason is because this current is upwards. What does this mean? Inductor current is going to be equal this dependent current source current, isn't it? Because they are connected in stereo. So if you write the Kirchhoff current law for this node, you see that. And I'm going to choose the resistor current reference like that. So if you write now Kirchhoff current law equation for this node, it's going to be IC. Since it is coming out of the node, it is plus, and coming towards the node, it is minus I inductor current, which is also equal to this current, plus this resistor current. This resistor current is, now this is the node voltage VC, this terminal. The other terminal node voltage is Vs. So VC minus Vs over 20 is IR equal to 0, Kirchhoff current law equation for this node. So if you remember that this impedance of the capacitor was 1/J omega C, 1/J omega is 10 to the power 4, and C is 10 microfarad. So this is minus 6, isn't it? So this is going to be minus 5 minus 1, so 10 goes up, 10/J is the impedance of the capacitor. If you remember the capacitor definition relation, which is opposite of this one, that means admittance, J/10 VC, capacitor definition relation. If I write it, VC is equal something IC, so that's going to be impedance. Impedance is this. Inverse of the impedance gives you the admittance. So this is admittance. That is impedance. Now I am going to write IC in terms of VC. It's going to be now J VC over 10, and IL is this current. So we said the coefficient now 1/40 1 over 40 VC plus VC over 20 VC over 20. So on the left hand side we've got minus VS over 20. On the right hand side it's going to be VS over 20. So if we put it VC parentheses, it's going to be J over 10 minus 1 over 40 plus 1 over 20 in parentheses VC is equal VS over 20. So if we multiply both sides by 40, it's going to be 4C minus 1 plus 2 VC is equal to VS. Multiplied both sides by 40. So this is going to give us 1 plus 4J VC is equal to VS. So VC is equal to over 1 plus 4C VS. So that's equal, if I multiply both numerator and denominator with the complex conjugate of this complex number, so let me do what I said, 2 times 1 minus 4C over 1 plus 4C 1 minus 4C. So this is complex conjugate of this one. So I multiplied numerator and denominator with 1 minus 4J VS. So what you get here, multiplication of two complex conjugate numbers. So maybe I'm going to make this not seen properly. I'll make it clear now. That is 4C. So complex conjugate numbers result is going to be real part square plus the imaginary part square, so it's going to be 17. In here I've got 2, 1, 5, 4C. So VS was 10, so it's going to be 20 over 17 and 1 minus 4J. So in order to transfer this phasor to time domain sinusoidal function, I've got to transfer it to the polar coordinate. So it's going to be 20 over 17. Modulo of that is the square root of 17. And e to the power j arctangent 4 over 1, isn't it? Which quadrant we are in, I'll draw it here now. So the imaginary, that's the imaginary, imaginary, and that's the real part. So negative imaginary is this area, positive real is this area. So we are, this complex number is in this quadrant, that's fourth quadrant. So I'm going to calculate this considering the imaginary and real part, both of them positive. So I'll find this angle here. To transfer it to that quadrant, I'm going to make it minus, isn't it? So it's going to be, that gives you 76 degree. So that's going to be 20 over square root of 17 e to the power j minus 76 degree. So roughly I can say that this is, if you say that this is 16, it's going to be 4, it's going to be then less than 5. So it's going to be in the range of 485 e to the power minus j 76 degree. So if I transfer now this complex number to time domain, VCT is going to be equal 485 cos 10,000 T. This doesn't change. You see, this is the same as this. The angle that I'm going to add is minus 76 degrees. So this is a particular solution. Since I said this circuit is stable, now since it is stable, homogeneous part is going to disappear in a short time. When this homogeneous part disappears, my general solution is going to be equal to particular solutions. So general is homogeneous plus particular. So I am saying that's going to go to 0. So general solution is going to be this particular solution. Now we are going to see this in the Proteus simulation, and then we are going to check our calculation whether it is true or not. So that is the end of this video then.